So we're gonna get some fun. Recap what we did. So last time we introduced Einstein's field equation. That was R mu minus 1/2 R G mu nu is made by G T mu nu. That is Einstein's field equation. And as I mentioned, this is the heart of this course equation. Just think that we have to spend half of the semester just for you to get the idea of what is written here. So, what are all these strange terms mean? We discussed about the complexity of this equation, right? It's a nonlinear equation made of the metric, first derivative, second derivative, contraction, second contraction. There are actually 6 independent equations written here. And non-linear, which makes it extremely difficult to solve. We have no way of knowing if we find all the solutions, except in certain cases where we do know some theorems. Under particular cases, we know that we found the right solution. Solution to this equation basically means, right, given the distribution of matter, how is that matter acts, or matter and energy, T mu is the matter energy and stress energy, and how is the space-time being curved? So how is matter acts to curve the space-time? This is the matter part, this is geometrical part. And we mentioned that we can add up a constant without changing anything. That will be the cosmological constant. If it's written here, lambda G mu nu, that's one cosmological constant. If we shift that, and because of the metric compatibility, that is automatically conserves energy. If we move it to that side, it's called dark energy. As a negative sign, which means that it behaves in a very different way than what you're used to from everyday life. We'll discuss that when we get to talk about kosmology. Then we spoke about symmetries. We said, okay, our best hope to find solutions to this equation, what we're aiming at, is to look for symmetries of the equation, for symmetries of the metric. And the way to do it is in terms of killing vectors. And we said that if we have an isometry means that we are moving from one location to another location and the metric does not change. And the easiest example to think of is a sphere. Easiest for me. Okay. I'm in this point and I'm looking at the metric on the sphere, and it's a metric. But when I'm moving from another point, the metric does not change. Right? And that is an isometry. I'm just making a transformation from point x to point x prime, and all the components of the metric are not changed. This is called an isometry. Really, it's a mapping from the manifold to itself. Okay? And the direction is as we said, directional derivatives are vectors, so the direction would specify a vector, which is the killing vector. So any vector that generates such an isometry is called a killing vector. And it obeys the killing equation, nabla mu k mu plus nabla mu k mu is equal to 0. That's the killing equation of vectors that generate the isometries. And along the trajectory, we have that p mu nabla mu k mu p nu is equal to 0. Namely, the momentum of a particle in that direction is conserved. The importance of a killing equation, the killing vectors, basically. We know that there are conserved quantities. We're going to see today how we're going to make use of them. And then the last thing we did was to start looking for a solution for the Schwarzschild solution. This great name, Schwarzschild solution. So we look for a solution for a metric. So first we look for a solution for Einstein's equation in vacuum. Which is simply R mu nu is equal to 0. Vacuum, no matter, so this is automatically 0. And if R mu nu is equal to 0, then automatically R is equal to 0. So that's enough. And we search for a solution which is static and isotropic. Isotropic means it does not have any preferred direction. So we use spherical symmetry. And we started to derive it, and we ended up using these two criteria, and then we add up a third criteria that's far enough from the central object. It will have to go back to Minkowskian, that's called asymptotic flatness. In fact, I did not fully use it, I just used the fact that it should have one negative eigenvalue, three positive eigenvalues. So let's call it pseudo-Riemannian. And we ended up that the most general metric that will fulfill these conditions would look something like Bs squared is a minus e to the power 2 alpha Tn R dt squared plus e to beta Tn R dr squared plus r squared d omega squared. Obviously, the omega squared is d theta squared plus sine squared theta d phi squared. This is a general form of the metric we're looking for, which is static and isotropic. We did not so far made any attempt to solve Einstein's equation. We just had a completely general discussion of such a metric. Questions before we continue to derive this metric? Yes?
Could you explain what is static and isotropic? I mean, is it the same also in the R direction, or is it isotropic?
No, isotropic just means that, okay, we will discuss that further down the line. Isotropic means that wherever I look, I don't have any preferred direction, right? If I'm sitting here in the class, I look to my left and I look to my right, I see different things. So space around me is not isotropic. But now imagine that you are on a small boat in the middle of the ocean. Now you're looking around you and you don't have any preferred direction. So you don't know which way to go. Right? Everything everywhere looks the same. That means isotropic. Right? Now, of course, it's isotropic only at the central point, right? It's not if you're in the vicinity of the central point, it's not isotropic because the potential will have a preferred direction. So it's not in the radial direction, of course, there is a difference. Isotropic means if I'm standing at the center, I'm looking around me, I don't have any preferred direction. I don't know where to go. Okay? Any further?
Also a question. The general equation, what are the methods of solving a general problem? Are there any, is there any software or something or numerical methods? Or we just accept a few symmetric solutions?
No, that depends on the problem. Again, we will not have time to discuss it this semester, but gravitational waves, for example, is a perturbative solution. Right? You have metrics which you know, and then you're making a small perturbation, and small perturbations, essentially it's a Taylor expansion of a known solution, you end up with gravitational wave solution. But generally speaking, yeah, how to solve it? You need to have intuition, luck, and today you do it with computers as well. Again, because it's non-linear, I don't know of any, but again, I'm no expert. There are people who are, as I said, there are people who spend their careers trying to find solutions. I'm not one of them. So maybe other people will know more than I do. Not here. Yes?
How do we find boundary conditions for this kind of equation? Because, well, we need them.
I state boundary conditions. Here I need to get physical insight. I cannot get it from the math itself. Right? My physical intuition says that if I have a source of gravity, right? This is again a vacuum solution, which I'm assuming that there is a source of gravity which is a small region in space. So my intuition is that when I get to R goes to infinity, I end up with a Minkowski space.
But where is this small source of gravity?
Well, I did not say where it is, just say it's in my vicinity. It's in some radius r away from me. Right? I have two coordinates, I have four coordinates, right? Theta and phi. I said theta and phi, doesn't matter which one. There are r and t. So I just said that there is a source of gravity, some radius r away from me.
But you're both saying we want to solve the entire space, right? Want to find a solution, and saying that there's some source of gravity somewhere.
Yeah, well,
The
you'll
source
see
of
that.
gravity
You'll see
has
that.
to be somewhere we don't
You're right that this solution is limited physically, and we'll discuss that. First, I'll introduce you the solution, and then we'll discuss the limitations of the solution. Okay? You're right. In a sense, for example, I can say it right away. Right? This solution will not be valid in the interior of the sun, for example, or interior of any star. Right? Because the interior of any star is not, you cannot say that it's a vacuum there. But outside of a star, it is a valid solution. Because if I'm outside, think of as an astronaut that orbits the Earth or the Sun, right? It is a valid solution. You'll see that.
But at some point, if you're outside the surface of the sun, some R's are less than the radius of the sun, the solution will not be valid.
If it is smaller than the radius of the Sun, then the solution will not be valid because it's no longer a vacuum.
So
But as long the conditions are that it's static and isotropic. So I didn't really ask what happens to the interior of the sun, for example. As long as whatever produces the gravitational potential will be static and isotropic, then it's okay for me.
Okay.
So, for example, if I have a star, right, produces gravitational potential, produce a solution, we're going to derive a solution. Now the star collapses. Okay, happens to stars. They collapse. But they collapse in a way which does not affect isotropy, and for me, the solution will still be valid. It's okay. I'm outside of the star. I still feel the same.
Okay, but since the solution is ceased to be valid as r equals radius of the sun, we need some boundary condition at this radius of the sun.
Yeah, I just need to match this solution to another solution which will be valid inside the interior of the star.
How do you find the solution in type?
Wait, let's find this solution first. You are jumping. Right now, I need to get physical intuition, right? So my physical intuition, and the only physical intuition that I got was that when I get to infinity, so infinitely far away from the source of gravity, right, gravitational potential, then I'm back to Minkowski metric, so I don't care about it, which makes sense. Yeah.
If it's vacuum T is 0, but lambda is not 0, is it still easy to?
No, again, this lambda we'll discuss lambda when we speak about cosmology. So actually I'll give it to you in one of the exercises. You'll see that for the values of lambda that we know, we measure, basically you can neglect that.
But it's not Minkowski.
No, it's not Minkowski. What? Yeah, this will not be a Minkowski. But it's a very small value. Okay? I mean, it seems to me that you're trying to look for mathematical flaws here, which maybe there are because I'm not in the math department. So but now we're focusing on physics here. I mean, I'm doing the math. Don't worry, I'm doing the math. But you need to get the physical intuition here. And you see that it works out in the sense that all these mathematical difficulties that you think of, they're not practically, you don't see them. When you do see them, I'll tell you that here it's not, it cannot be valid anymore. Okay? Okay, so as I said, what we derived here, this point here, we did without any attempt of solving Einstein's equation. We just made the general considerations of how the metric should look like in a static anisotropic metric. Now, if we want to proceed, we don't really have too many options. We now actually have to do it with our hands and say, okay, this is the metric that we got, so now we do have to plug it into Einstein's equation. This is Einstein's equation. So now we do have to plug it in. So I'm just going to write it down. This part is something that you can do using Mathematica or your favorite.
Didn't use those static.
Yeah, I did not use it yet. I'm going to use it now.
Does that mean it's derivative of alpha?
The time derivative is going to be equal to 0. That's the static. You see that?
Time or proper time?
What?
The time meaning t, right there, right?
Yeah, yeah.
Not
I have
proper time.
No, time. This is a metric. When you say proper time, we're talking about a certain observer in image. Now, a certain observer that is doing something, test particle, test observer. Now I'm talking about the metric. The metric is general, right? G mu nu is general. Don't get confused. Things can be confusing. All these terms. So, I'm going to use now 0, 1, 2, 3 instead of t, r, theta, and phi. And now we're just plugging it in into Einstein's equation. So just have to calculate. So this is our metric. So if this is our metric, we need to calculate first Christoffels, so all the components of the affine connection. So we got that gamma 0, 0, 0 is d0 alpha, gamma 0, 0, 1 is d1 alpha, gamma 0, 1, 1 is e to the power 2 beta minus alpha d0 beta, gamma 1, 0, 0 is e to the power 2 alpha minus beta d1 alpha, gamma 1, 0, 1 is d0 beta, gamma 1, 1, 1 is d1 beta, gamma 2, 1, 2 is 1 over r, gamma 1, 2, 2 is minus r e minus 2 beta, gamma 3, 1, 3 is 1 over r. Of course, you switch, you get the same, right? The two lower indices. Gamma 1, 3, 3 is minus r e minus 2 beta sine squared theta. Gamma 2, 3, 3 is minus sine theta cosine theta. And gamma 3, 2, 3 is cosine theta over sine theta. Cotangent theta. That's what you do.
And the rest are 0?
The rest are 0 or equal if you're switching by series. Fully honest, I did not derive. Normally, I derive all the equations that I put you when I first derived them. These ones I did not derive, I just copied from the textbook. So I believe the textbook is wrong. But it's very easy to check. Modulo algebraic mistake. Okay, now you do that, and then you take the second derivative and plug it into the Riemann.
And all the d0 is 0.
d0 is dt.
Zero.
What? Yes, wait, just a second. We'll get there. But what we care about is the r, is the Riemann. So r 0, 1, 0, 1 is e to the power 2 beta minus alpha d0 beta squared, or d squared 0 beta plus d0 beta squared minus d0 alpha d0 beta plus d1 alpha d1 beta minus d1 squared alpha minus d1 alpha squared r 0, 2, 0, 2 is minus r e minus 2 beta d1 alpha r 0, 3, 0, 3 minus r e minus 2 beta sine squared theta d1 alpha r0 2 1 2 is a minus re minus 2 alpha d0 beta r0 3 1 3 is a minus re minus 2 alpha sine squared theta d0 beta r1 2 1 2 is r e minus 2 beta d1 beta r1 3 1 3 is an r e minus 2 beta sine squared theta d1 beta, and r2 3 2 3 is a 1 minus e minus 2 beta sine squared theta. Okay, that's what we got. Still not enough. What's the next step? The contraction, right? I need to do the contraction to get the Ricci tensor. So I'll have to do that.
This is the method that Schwarz should use? Or we don't know?
I think so, best of my knowledge. I mean, I guess this guy now was sitting there.
We also copied it from the textbook.
I don't. I think he wrote it. He's the one that. I think he had plenty of time, right, lying there, you know, or in the support.
They didn't know yet about black holes, so I thought.
There's no black hole. Wait. I guess he had plenty of time, he had papers and pens, and instead of writing for his whatever wife or what, it's just sitting down there, lying down there, solving these equations. So now you take the contraction to get the Ricci tensor, and you get an R00 is d squared 0 beta plus d0 beta squared minus d0 alpha d0 beta plus e to the power 2 alpha minus beta d1 squared alpha plus d1 alpha squared minus d1 alpha d1 beta plus 2 over r d1 alpha. R11 is minus d squared 1 alpha plus d1 alpha squared minus d1 alpha d1 beta minus 2 over r d1 beta plus e to the power 2 beta minus alpha d squared 0 beta plus d 0 beta squared minus d0 alpha d0 beta. R01 is 2 over r d0 beta. R22 is e minus 2 beta. R d1 beta minus d1 alpha minus 1 plus 1. And R33 is R22 times sine squared. After a long algebra, if you have a few hours, I guess you can also do that. There's nothing really that prevents you from doing that. Right? You got the components of the Ricci tensor. And now what is left is to plug that in Einstein's equation with vacuum, which is written here. We just take all of these equations, equate them to 0. But actually you don't need to work that hard. Right, so if we write this is equal to 0, then automatically we get that d0 beta is equal to 0. then if we take that one and take the time derivative of that, so d0 of that, and use the fact that d0 beta is equal to 0. Right, so that we get that. From that we take the time derivative and use the fact that this is equal to 0, d0 beta is equal to 0. And we have, a minus d0 beta, d1 beta, that's going to be equal to 0. The only thing that is left is d0, d1 alpha is equal to 0. So if d0 beta, let me write it down again here. Remember the metric we had was ds squared was at minus e to the power 2 alpha dnr dt squared plus e to the power 2 beta of dnr dr squared plus r squared d omega squared. So if d0 beta is equal to 0, what does it mean? Right, so beta is just a function of r. Beta of r. Here we have alpha, we take the derivative with respect to r and respect to t and is equal to 0, which means that what? We can make a separation of variables, right? So we can write down alpha is some function of r times plus some function of t.
We assume that everything is not dependent on t.
No, we have that. No. We reached that alpha and beta are a function which we need to determine.
But why aren't we looking for solutions that do not depend on t entirely?
They will not depend on t, yeah, but we don't see it right away.
Why don't we do that as an assumption?
No, because we look for a general solution right now.
We assume static case. So where we say
No, okay. That's the thing you don't see. Static case. Okay, you know what? Give me 10 minutes after we finish the derivation, and you'll see that. Okay? I'll answer it. I'm not going to. So here we have e to the power 2 alpha. Right? It's really minus e to the power 2 f of r, e to the power 2 g of t, dt squared. Right? But t is just a time coordinate which is completely general right now, so we can simply redefine it by multiplying it to the e to the power g. Okay? So I can always redefine t. So dt, redefine, dt would be e to the minus g of t dt. Right? Which is equivalent of selecting g of t such that it's always, selecting the coordinate t such that g of t is always 0. Okay? So what we have, so redefine that, meaning that equivalent of selecting g of t equal to 0, which means that we're left with ds squared is equal to e minus e to the power 2 alpha only of r, and that's the meaning of static here. Dt squared plus e to the power 2 beta of r, dr squared plus r squared d omega squared. So what it means is that what is that part? This is the component that multiplies, this is gtt, right? This is what multiplies the time coordinate. And it is independent on t. In fact, there is no component of the metric that depends on t. Okay? And if there is no component of the metric that depends on some coordinate, what does it mean? It's a?
Isometry.
It's an isometry, right. So we have a
Killing vector.
killing vector. That's right. So a spherically symmetric static metric has a time-like killing vector. Right, that's what we just proved.
Could you repeat that?
Yes, again. So we found out that none of the components of the metric, right? This is GTT, this is GRR. Right? None of the components of the metric depend on the coordinate t, which means that t is an isometry. Right? We said if we have a metric which one of the coordinates, none of the components of the metric depend on a certain coordinate, then there is a killing vector in the direction of this coordinate. Right? We said that last time. So we said basically any spherically symmetric vacuum metric possesses a time-like killing vector. Yes.
So all metrics dependent on some coordinate t.
Yeah.
You don't know, so you don't really know that this t coincides without time. You don't know,
T is a coordinate. Yes.
We don't know this is time.
Right now, still not. We'll get to that.
Okay.
I'm only halfway through deriving on the metric.
Okay.
Okay. Now,
So time-like killing vector.
it's a time-like killing vector. It's just that time is the coordinate
Okay.
time.
Yes.
Now, whether this is the same time as our coordinate, well, the answer is obviously yes, but we have not proven it yet. You're right. Okay? We will prove it. Don't worry.
We made a transformation to choose time.
Yeah, we just absorb it into that.
From one time to another time.
Yeah, I have not finished the derivation. Wait until I finish the derivation and you'll see it. Right. Now, a metric that possesses a time-like killing vector, the technical name is called stationary metric. This is a stationary metric. Okay. Now, there is also a metric which is called static. A static metric is a metric that the killing vector is orthogonal to a family of hypersurfaces, which essentially represent a constant time. In a more simple words, that it may have a cross terms, the form dt, dr, dr, dt. In an even simpler case, a simpler thing to think about, right? For example, the metric that the sun has in the solar system, well, it's both static and stationary. The Schwarzschild metric is both static and stationary. But the difference between static and stationary can be thought of as the following. Stationary is fixed, so, but it enables motion in constant, in a fixed way. Right? For example, the Earth is fixing the sun in a constant velocity. This is static metric. Stationary metric. Static metric, everything is frozen. It's a bit more. What I said is not a perfect analog, so don't get you here. Because the correct way is that the static metric will not have. My apologies. Is that the static metric will not have a cross term. Cross term you have, for example, in a Kerr metric, where there's a region near the black hole which is forced to rotate with the black hole. But we will not discuss that in this course. Right, so this is the technical term, stationary metric. Okay. Yeah, another simple way of look at the difference between a stationary metric and a static metric. A static metric is stationary plus you can reverse the time. If you go t minus t, nothing changes. maybe that's it. This one.
Stationary or static?
That's a static. Stationary is any metric that has a time-like killing vector is called stationary. But that, again, things can change, but in a constant way. Right. Anyway, the Schwarzschild solution is both static and stationary, just side to mainstream. And so static is that the time-like killing vector d0 static d0, it's a time-like killing vector, is orthogonal to the surface t equal to constant. Yeah.
I'm not sure I'm right. It's just what I think I understand from what you're saying, that static is that when the matter is static and not moving and remain in the same place or stationary, the matter could be moving but without changing the density.
It's not the matter, it's the metric. It's not the same. That's why I'm saying what I said is easy to think of, but it's not exactly accurate. The accurate way, this is the accurate description. Right? Time-like killing vector, meaning none of the coordinates depend on time, is called stationary. Static means that there are no cross terms, because you could have a metric that also has terms of the form like dt dr plus dr dt, right? Something grt, which will not be dependent on time. Right? It could depend also on r or theta or something else. I could have them. I don't. Right? I'm not sure that we should get into that. Maybe I'll ask Akshay to say some words about that in the tutorial. By the way, given that everybody here agreed, then we'll make the next tutorial on Sunday after the lecture, right? So lecture is 10 to 12, then at 12 to 1 have a 1 hour tutorial with Akshay.
What will the tutorial be about?
What?
What will the tutorial
I don't know yet. I have to think. I haven't decided. If there is something which you want that to practice on, then you can tell me, and then we can ask to prepare something. Okay, never mind. Let's continue to develop the metric. It's just fun, right? I mean, the metric essentially will describe a non-rotating black hole, also anything outside of the star. If the metric is just stationary but not static, namely there are some terms like that, this is a rotating black hole. This is the curvature. It has its own interesting phenomena, but unfortunately we will not have time to discuss in this course. Okay. Now, you got the idea? So let's move on. We got that as a metric. It's a general form of the metric, so I can simply remove the t here. So we get an r. And let's continue to develop the metric. So we still have r00 is equal to 0. R11 is equal to 0. And what I can do, I can multiply them. So I have a 0 is equal to e to the power 2 beta minus alpha r00. So I have here, this goes down, plus r11. When you plug it in, you'll see that mostly they cancel out. The only thing that do not cancel is this one, 2 over r, d1 alpha there is a minus here, so that's okay. Plus d1 beta. So if this is equal to 0, what does it mean?
Alpha equals minus beta plus constant.
That means that alpha is equal to minus beta plus constant. And again, we can get rid of the constant by rescaling the coordinates, right? We can just put that constant here and absorb it into the coordinate r. And so we can simply write down alpha is equal to minus beta. Into the definition.
That means that Jacobian is not dependent on R.
No, it will be because alpha is a function of r. But the constant here I can just absorb inside r.
You can now know the Jacobian. It's just
Not
R
yet.
squared, it's just the regular one.
Yeah, not yet because I don't know what is alpha and beta.
Okay, they cancel out. When you
If they can, okay, yeah, in that case it is. But it doesn't really matter here. So now the last thing that is needed really is to use R22 equal to 0. And since alpha is equal minus beta, then we have e to the power 2 alpha 2r d1 alpha plus 1 is equal to 1. Which is the same as writing d1 r e to the power 2 alpha equal to 1. The solution to that is quite straightforward, is e to the power 2 alpha is 1 plus some constant mu over r. Mu is just a constant right now. So, using that insight, plug it back again in the metric, and then the metric obtains the form is that ds squared is minus 1 plus mu over r dt squared plus 1 plus mu over r minus 1 dr squared plus r squared d omega squared. Now we still don't know what is this constant mu. That's as much as we can go because the other equations r0, 0 equal to 0, r1, 1 equal to 0 will be automatically satisfied by this metric. So how do we determine the constant mu? And that also answers your question. Exactly, weak field limit, right? So now we attach that to what we know about the weak field limit, which you already derived, right? So in the limit r goes to infinity, we know that g00 r goes to infinity is equal to what? That's mu of r. G11 r equal to 0.
1 minus mu over.
Right. Taylor expansion. So power minus 1 here. But we also know that the weak field limit we've already derived. We had G00 was a what? Remember?
1 plus
Minus 1 plus 2 phi. And G11 was a 1 minus 2 phi. Right? What is phi? gravitational potential. Phi is a minus gm over r. So we get the same result, which also explains why I can use r and t as the coordinates. If I associate mu, it's minus 2 gm. So when I do that, I finally get the very famous Schwarzschild metric, which is d squared is a minus 1 minus 2 gm over r. Now, just to make sure that you're all with me, I'm adding up the c terms. C was equal to 1, so there's a c squared here really. C dt squared plus 1 minus 2 gm over r c squared to the power minus 1. R squared plus r squared d omega squared.
Still didn't answer the question why T is the time.
It is, because I matched it to what I know in the weak field limit, in the asymptotic limit.
This metric implicitly says that there's a point mass at, not a point mass, there's some mass at the mass of an m mass at the origin, right?
Wait.
Because phi is derived from
Okay, hold on. Let's. What we have here, this is the correct metric that describes a spherically symmetric vacuum solution. So, spherically symmetric vacuum solution to Einstein's equation.
Or when you're constrained on R.
Wait. Now m here in principle is a parameter, right? Which is associated with the mass. What happens when m is equal to 0? Minkowski, right? When m goes to 0, we get back Minkowski. What happens when r goes to infinity? Also Minkowski. That's the asymptotic flatness. Now, so this is static. The thing that maybe answers your question. We did not say anything about the source, right? We said it has some mass m, but this is really a parameter. The only thing we care about is that the source is spherical. So again, if the source, in fact, we didn't even specify that the source itself, it doesn't have to be static. The source can do whatever it wants. As long as it keeps symmetrical. So, example, if we have a star, we are outside of the star, right? And we feel something, and now the star collapses. How does that change the metric? Nothing. It does not change. The metric remains the same. If you are, I don't know, orbiting a star in some expedition, then suddenly the star starts collapsing, you're not going to feel anything.
Assuming the mass does not change.
Assuming, yeah, the mass is the same. Assuming it's spherical. Assuming it's spherical, the only assumption was it's spherical. If it starts to, leave, it's not spherical anymore, then yes, the metric will change. Now, there is a theorem, I mentioned that to you last time, that it's a uniqueness theorem, saying this is the only vacuum, spherically symmetric solution in vacuum, and the theorem is known as Virchow's theorem. So, Virchow's theorem says that the Schwarzschild metric is unique. It's the only metric that describes spherically symmetric vacuum solution. In fact, as I mentioned it to you, we went through most of the path through proving this theorem, but not all of it, because I don't think it's crucial. Yes.
We have it in vacuum, right? So the m is the mass of the test particle.
No, m is not the mass. M is the mass of the source that produces the.
So we have a source in a vacuum.
Yes, the source is outside of that realm, right? You are outside of the star.
Okay.
This is the sun. This is causing the potential. Now you're an astronaut, orbiting. Doesn't have to be the sun, orbiting the Earth.
Okay.
Right? Around you is a vacuum. So the metric is true everywhere outside of that star.
Okay.
Okay? Now the mass is m.
So
Okay.
if you have like two different radical spheres and both have different m's, how do you measure that?
This is not a true solution anymore.
Okay.
Right? If I have two stars, like two neutron stars, for example, that rotate each other, this is not a spherically symmetric solution anymore. I have to use a different metric, and that becomes really hard. Right? Then I can start to do some. If the stars are very far away, then I can do a perturbation, saying, okay, this is around here. I have a Schwarzschild metric, but there is some influence for that.
Yeah. Okay, so outside it, like really far away, you can just
Really
say
far away,
it's
I can.
really,
Yeah.
it's
This is, of course,
somehow.
this is mathematical approximation, right?
Yeah.
Because it's just for a single source that have vacuum that produces a gravitational potential, and we are outside. Okay? So again, this is an important point because it's very confusing. I was also confused by that when I first studied that. We have a star that produces the potential. The solution is not valid, of course, inside the star. Why not?
Because it's not.
Because T mu nu is not zero inside the star. But it's valid everywhere in all the space outside of that star, as long as the star is spherically symmetric. The solution is correct everywhere except inside. Yeah? More questions about it? And that's a very important point because it's very confusing. More questions about that? Yes.
But if there are gravitational waves in the metric, it's still valid.
There are no gravitational waves. I'm not talking about gravitational waves. It's a different solution.
But the theorem excludes that.
Yes, it's not symmetric. It's not spherically symmetric. You get gravitational waves you get when you are accelerating or some masses. Classical example where you see them, right? When you have two neutron stars or black hole and neutron star, they orbit each other, right? If they orbit each other, right, this acceleration, it's angular acceleration, then they emit gravitational waves. Gravitational waves are perturbations, essentially. And then when you have this thing that accelerates, it's no longer spherically symmetric. Okay? Again, we're doing the simple thing. Understand the simple thing, we'll go to the. Well, we won't go that far because we don't have time. The semester
The
will be over.
collapsing star will not create gravitational wave.
What?
A collapsing star will not create
It
gravitational
will, but much less. But essentially, it will depend on the.
If it collapses symmetrically.
If it's symmetric, then it will. Look at the solution. Other.
The metric is not it's for somehow.
Right. So what do you see when you look at it?
Sometimes it's zero. The
What?
coefficients of
You see that there are two radii of interest. There are two radii which something Doesn't look good. What are these radii?
0.
Right, so you have r equal to 0.
2gm.
And it's 2gm over c. Right? R equal to gm over c. Something bad.
What? C squared.
C squared. C is 1. Right, so something may go wrong. Does it have to go wrong? No. Why not?
If they're
It's at the
outside,
start.
Right?
if they're outside our scope.
What?
If they're outside where we solve.
No.
Depends on the
No, I meant something else. Mathematically speaking, right? It looks like a problem, but it could be an artifact.
If you have a star and it is inside the star. So
No, I'm not talking about that. I'm talking mathematically now.
You chose the coordinates.
I chose the coordinates, right?
You could choose another one.
Right. I chose the coordinates. For example, right? I can describe Euclidean two-dimensional space using spherical coordinates, right? I can write down ds squared equal dr squared plus r squared d theta squared, right? And that's fine. There's nothing is problematic, right? But then what happens? What is g theta theta? It's r squared, right? What is the inverse? G theta theta? It's 1 over r squared, right? So that means that if I try to calculate the inverse of g at r equal to 0, I get infinity, right? But this is not a real infinity. In the sense, I mean, it's a real infinity mathematically, but it doesn't mean that anything bad happens to the metric at r equal to 0. Just my choice of how I chose the coordinates, right? So we might be facing the same issue here. We might be seeing something that looks strange, but this is just because we selected coordinates which we think are good, but maybe they're not so good. Okay? So what do we do? How do we check that? So we need to find a way which is coordinate free, basically, to tell us if these radii are
But and that's true for r equal to 0. For r equal to gm over c squared, you have the problem with becoming from positive to negative. Which is
no, again, this could be an artifact of the
it's
coordinates.
saying there. Okay.
I can choose something else. What if I choose x, y, z? I didn't have to choose r. Right? I can choose whatever. Right? So you want the correct answer, what you really need to do is to find some scalars and look how they behave. Right? Now the richest scalar is not good. Why not?
It zeroes out.
It's always 0, right? Because the r mu nu is always 0. So the rich is always 0. So what we look for is another scalar. So to see if there is a real problem, real problem, we look at scalars, coordinate independent. No, yeah, there is a lot of math behind it, which I'm going to skip. The scalar that we care about is called a Kretschmann scalar. So Kretschmann scalar, called K, and it is really R mu nu rho sigma, R mu nu rho sigma. That's the name. And you can do the calculation. And what you'll find is that R mu nu rho sigma, R mu nu rho sigma is 12 g squared m squared over r to the power 6. And that means the following. R equal to 0, there is a real issue. That's called a singularity. So this is a real singularity. essentially, this is the end of known physics, classical physics. Now you can start going to quantum mechanics and start quantizing space and see if you get something different. Right? At r equal to gm over c squared, really nothing special for the coordinates happen, in a way.
So we can transform our coordinates.
Exactly. So we can choose different coordinates, and in fact we are going to do that. We can choose another set of coordinates, which I will show you how to do. That's called Kruskal coordinates. So not a real singularity. We will derive it likely next week. That's called the Kruskal coordinates. It will show you that in some basic sense nothing special happens to the coordinates at this point. But something does happen here. It's not true to say that it's just some art. But something physically does happen here. So this radius has a name. You know what's the name of this radius? It's called the Schwarzschild radius. Another name is the event horizon. And there will be time to discuss that. You'll have to wait patiently. Likely a few more lectures. That's called the Schwarzschild radius. Radius is called also denoted as RS.
W missing right there.
What?
There's a W missing after the H.
Gosh, yeah. Okay, yeah, you get the idea. Schwarzschild radius. Now again, you have to be careful in how you treat it, right? And as we mentioned, we already discussed it, right? If we look at our own sun, for example, do you know what is the Schwarzschild radius of our sun? Well, you can easily calculate because it's linearly depending on only one thing, which is the mass of any object. But everything else are physical constants here. So just to get you the feeling, right? So the Schwarzschild radius of the sun. Does anybody know? Happen to know?
3 kilometers. 3 kilometers.
Yeah, something like that. That's right. It's about 2 kilometers. Yeah, 3 kilometers is good. Yeah. So for sun, m sun is 2 times 10 to the 33 gram, and therefore Rs of the sun, which is 2 gm sun over c squared, is 3 times 10 to the 5 centimeters. Working centimeters. Right. What is the radius of the sun? No?
Much more than
7
million kilometers.
Yeah, 7 times 10 to the 10 kilometers. Centimeters. We always work in centimeters. CGS. Right? Which means that it's something like 5 times 10 to the 5, maybe less. 2 times 10 to the 5 are Schwarzschild of the sun. So again, when we are talking about the solar system or anything in the vicinity of the solar system, there are no singularities, right? And if we try to describe the metric, right, the GRR here, right, it will act like that outside of the sun, but once you reach the surface of the sun, this solution is not going to be valid anymore.
לכן אנחנו מניחים שכאילו T הוא זמן כמו שאנחנו מכירים אותו ו-R הוא כמו שאנחנו מכירים.
Okay, no, this is because we said asymptotically reach down. Okay, so most objects that we know of, their physical size is greater than the Schwarzschild. Right, so we don't really care. So that means automatically that this solution is not valid, right, inside the interiors. But there are objects which their size is smaller than the Schwarzschild radius, and that these are called black holes, right? And we'll discuss these objects. Okay, so black holes, our black hole is smaller than our Schwarzschild, RS. discussed. It's going to look like this.
You go, well, test particle. What happens if a test particle or you or something goes into the sun, into a radius closer to the center of the sun than the disruption radius? What experience effects is similar to
It's
black
not going
hole?
to be. Not because
Because most of the mass is outside.
exactly. Think of it in Newtonian terms, right? You look at the Newtonian potential,
Oh, okay.
right? When you get inside, I mean, the masses and the size cancel, so you just care about the mass that is enclosed inside the racks. So this just to get the to get the idea, right? So you don't need to worry about black holes if you don't sleep at night because you might fear that the black hole is going to swallow us up. No, it's not going to happen. No way. There are other things to worry about. Okay. Good. We'll get to that. That's one of the exciting parts of this course. We'll get there. We won't miss it, but first thing first. Questions? So the next step is to look for, start to explore this metric.
One question.
Yeah.
We want to explore this metric, for example, calculate trajectories of light, maybe.
Yes.
But Einstein did this before he knew that.
Before what?
Before he knew that metric.
No, really not.
Einstein predicted light deviation around the sun. No.
Deviation of light can only be after you solve Einstein's equation. Einstein's, just historically speaking, right? Einstein wrote down his equation in 1950, right? Special relativity in 1905. Einstein's equation 1915. Schwarzschild's solution, the first solution was 1916, so 1 year later. And then what you talk about is the famous, when Einstein became a hero and they saw the bending of the light, that was Eddington, that was 1919, several years later.
But he sent people to investigate it even before that. I mean,
No. The famous expedition that shows that light is the deflection of light was Eddington, Otto Eddington, who was the famous astronomer of the time, 1919.
but
Nobody
there were-
thought about deflections of light before he was
There's a
told.
famous story that he sends his German friends to Turkey, and they were captured by the Russians, and this was before the first.
I'm not aware of that.
Okay.
Maybe it could be any time after 1916.
No,
After
no,
the
this was
project.
before the World War. This was the break of the World War. They were
There
jailed
was I'm not aware of this story.
Okay.
But maybe Einstein had it in his mind earlier. It was published in 1915. So, maybe Einstein knew about it before. I've got no way of telling because you can only read what is written. But there's no, to the best of my knowledge, there's no documentation of anybody knowing that before. Maybe Einstein had some idea. It took him 10 years to develop this equation. He had some ideas about various things that could happen, but the equation itself, the solution itself, was done, produced to the public when I said. Okay, so what we're going to do now is to explore this. Explore this metric means that we're going to look for. Sorry. I'm doing quite well, which means that I'm going to post you the next problem set today, but I think next week maybe we'll get 2 problem sets. Or 1 long one. So
We'll have more time to hand it, right?
what?
We'll have more time to usually hand it.
I get 1 week with me.
For
Look,
both
if you-
assignments?
1 week from the time I said that. If you need extra 2 days, you'll get extra 2
And
days.
if you post 2 assignments in the same week, we'll still get
I can put it in 1 file to like 1 assignment.
Wait,
Makes you
it's
feel better.
2 times long. It takes 2 times. Like,
Come on. If you have this problem, I mean, people have asked me to give them like a few extra days. I give you a few extra days. That's not a big thing. The important thing is that you solve them, right? And the reason is that, and you do it by yourself. You don't copy from your friends. Okay. Motion of particles. Particles in Schwarzschild geometry. Okay. What do we do? For the same motion of particles, geodesic, right? So the first thing to do, of course, to solve the solve the geodesic equation.
Have a killing vector, so maybe
Yes, that will be the second thing we do. We start with the stupid thing. The stupid thing is to try to solve the geodesic equation heads straight, right?
it's a bit complicated.
It is, yeah, you got it right. So if we simply, right, I just write it down for you. Right, so writing down all the Christophels, we basically did that, but now we know what are alphas and betas. So the Christophels will be a gamma 1, 0, 0 is a gm over r cubed, r minus 2 gm. I omit the c. Gamma 1, 1, 1 is a minus gm over r minus 2 gm. Gamma 0, 0, 1 gm over r minus 2 gm. Gamma 2, 1, 2 is a 1 over r. Gamma 1, 2, 2 is a minus r minus 2 gm. And gamma 3, 1, 3 is a 1 over r. Gamma 1, 3, 3 is a minus r minus 2 gm sinus squared theta. Gamma 2, 3, 3 is a minus sine theta cosine theta, and the gamma 3, 2, 3 is a cotangent theta. Okay, that's what we get. How many geodesic equations we have? 4. Right, so the geodesic equations. One for each coordinate. Right. D squared t over d lambda squared plus 2 gm over r minus 2 gm. The r over d lambda, dt over d lambda is equal to 0. For r, we have d squared r over d lambda squared plus gm over r cubed, r minus 2 gm dt over d lambda squared minus gm over r minus 2 gm dr over d lambda squared minus r minus 2 gm d theta over d lambda squared plus sine squared theta d phi over d lambda squared is equal to 0, and then d squared theta over d lambda squared plus 2 over r d theta over d lambda dr over d lambda minus sine theta cosine theta d phi over d lambda squared is equal to 0, and finally d squared phi over d lambda squared plus 2 over r d phi over d lambda dr over d lambda plus 2 cotangent theta d theta over d lambda phi over d lambda is equal to 0. Looks nearly hopeless to solve. It's doable. Okay, computer, it's definitely doable. But it's nearly hopeless.
How is that?
What?
How is that doable?
How is that doable?
It's a nonlinear equation.
It's a second order differential equation.
Yes, but the Einstein equation is also a second order differential equation.
No, actually, it's more complicated. This is
Four equations.
these are 4 equations.
Nice.
There are solutions right now.
Instead of 6
No, it's obviously there need to be a better ways. Actually, we are going to solve this, but we're going to use some physical insight. Yeah, of course, killing vectors. How many killing vectors does this? How many? 4. Which ones?
Time, the A is the theta, and I guess also R in some way.
No, we don't know.
-3.
You have at least for T and for phi, right? From the geometry.
Yeah.
No.
-3 kilograms.
Yeah, you're right. Yeah, 4. Okay, let's do it one. So we look for killing vectors. 1 for time is going to give us a what? A summation of what? Energy. 1 is for phi. Well, 3 are for phi. Right? What will they give? A summation of angular momentum. Right? Angular momentum, because we don't have a preferred direction here. So conservation of angular momentum means what? We have 1 direction and 2 angles. Right? 2 angles meaning what?
Motion is in the plane.
Motion is the plane. Right? It's the same as Keplerian motion. Did you analyze Keplerian motion in your... I don't know who studied with me mechanics. But did you analyze the Keplerian motion? Because we're going to do now the same, only with the Schwarzschild metric. Okay, first at a time, right? One thing. So we're going to use the following tricks. Not tricks, shortcuts. It's not trick really, because it's all. So the shortcuts we're going to use. Killing vectors. We have 4. We said. What? 3, 1 will be for the spherical symmetry, right? Because we can rotate whichever direction, we don't care. Right? We have 3 directions.
So 3 from phi and 1 from T?
Yes. Right. We have a spherical symmetry. No, you can select whatever you want.
Symmetry means 2.
3.
Why not?
Because you have 3, it's a sphere.
Sphere, we have a theta coordinate and a t coordinate.
Again, you have phi, you can put phi wherever you want. You can put phi along the z direction, you put phi along the x direction, or along the y direction. You can rotate it whatever you want. So 3 for spherical symmetry. We have 1 for time. And if k is a killing vector, then we have that k mu dx mu over d lambda is constant.
Well, we have the mx.
Now we also know that along the geodesic, right, using the metric compatibility, we can write it down as g mu nu, or minus g mu nu, dx mu over d lambda dx nu over d lambda is equal to epsilon. Epsilon is a constant. Right? Epsilon is equal to 1 for massive and 0 for photons, or 0 massless. This follows from the metric compatibility. Along the geodesic. Remember the covariant derivative? one of the definition, the last definition for geodesic that I gave you was that the vector is parallel to itself. So covariant derivative would be a 0. Plug it in and you get that. Or simply put here tau. See, u mu is equal to this constant. All right, we're going to use that now. Okay, do have to. I will go back to that, but I'll have to erase them now. What? No, if it's a massive particle, it's a 1. Think of it for a second.
Follows something like the conservation of the inner product?
Essentially, yes, it's along geodesic, you have conservation of momentum. Okay. Now we said this would be conservation of energy. This would be conservation of angular momentum. So we have direction of angular, so conservation of angular momentum. Angular momentum is a vector, so it has a direction and a magnitude. So conservation of the direction of the angular momentum, we already said that, means that the motion is going to be on the plane. I can put this plane as the equator, so theta equal pi over 2. All the planets nearly are along one equator. What?
The Milky Way. What's the Milky Way?
It's called
Okay.
I don't know the English name. Give me a second, I'll remember. Mishor Milka. I don't know the English name. I don't remember. Which means, of course, that the theta over the lambda is 0. Theta is constant. So the other two killing vectors, this is two killing vectors. Other two killing vectors would be one conservation of energy, one conservation of magnitude of the angular momentum. What is the conservation of energy? This is a time-like killing vector. How does a time-like killing vector look like? Okay, mu. What? 1, 0, 0, 0. Right? What's the conserved quantity? K mu is a K mu, G mu nu. Right? What do we have here? It says a minus of 1 minus 2 gm over r. That is it. And then k mu dx mu over lambda is a what? Is a 1 minus 2 gm over r dt over the lambda. That is a constant, right? I call this constant E. Right? This is a constant of motion. What about the angular momentum conservation? Magnitude of angular momentum. So L is really fine. Zero, 0, 0, 1. L mu. It's L mu. So L mu is what?
R squared sine theta.
Very good. What is sine theta? 1.
Oh,
It's 1. So the conserved quantity is R squared, right? D phi over d lambda is constant, which we call L. Yeah, it's for test part of a unit mass. Everything should be divided by the mass. But again, it's just can absorb it into the definition of E and L. So you write it, E is the energy per unit mass, and the L is the angular momentum per unit mass. What is that? You've seen this equation before. What did you call it? What?
R cos theta.
What? Oh, we had a name for this equation. You said you learned with me. I showed it to you. I know. If you didn't know, this is Kepler's law. This is Kepler's law.
It's the first one.
Actually, it's the second.
Is it about the conservation of the...
הראשון זה של מעגלים, השני זה השלישי זה הקשר בין טאו ל-T
School isn't. So we're working quite hard. I promise you, everything is going to make perfect sense at the end. Let's see if we can. Okay. So now we have enough to start solving particles trajectories in Schwarzschild metric. So what I'm going to do now, I'm going to write down this equation specifically, explicitly. For theta equal pi over 2. Then we have here minus g00, so we'll have minus, I'm going to move here. Minus, so we're going to write it down as a minus 1 minus 2 gm over r. Forget about the c squared, right? dt d lambda squared, right? So I just expanded. Right? I only have 4 terms, really. Well, 3, because d theta over d lambda is going to be 0. So g00 is a minus 1 minus 2 gm over r. g11 is a 1 minus 2 gm over r minus 1. Right, dr d lambda squared.
Squared.
What? Plus, oh, no, I'm good. R squared d phi over d lambda. Squared is equal to 0. Oh, I didn't forget it. Sorry, it should be equal to minus epsilon. Epsilon can be either 0 or 1.
Should be squared. The coefficient of the
Right. No, no. G00.
Oh, okay, okay. The J0 squared.
G00, G11.
Y minus.
I just moved the minus from here and put it here. Just a constant, so it doesn't really matter. So I now multiply that by 1 minus 2 gm over r. And I get minus 1 minus 2 gm over r squared dt over d lambda squared. So that is really a minus e squared. plus the R over the lambda squared plus 1 minus 2 gm of R times, this is really L squared over R squared. And I have the epsilon here, so I'm adding an epsilon. Is equal to 0.
Where is the T over the lambda? In E squared?
Sine.
Oh,
Definition of E here. So this I can write, or I can write it as 1/2 the R over the lambda squared plus V of R is equal 1/2 E squared, where V of R is 1/2, I'm just expanding it, 1/2 epsilon minus epsilon times gm over R plus L squared over R squared minus gm L squared over R cubed. So although it's written like an expansion, Lorentz expansion, it's not really. This is complete. No additional terms here. It's everything. Why did I do it like that? What do I get?
Like it's effective.
Right. Again, this also you've seen. This is a what? That's a equation of motion in 1D of a particle in an effective potential, V of R. Now don't get confused, right? The real motion here is a 2D motion, right, in a plane. But I could write it down in a way which is easy to analyze. And I think we're running out of time, so we'll do the analysis only next week. This is very similar to what you already did in your first year's mechanics, right? Also there we took a motion of a trajectory of a particle and we look we analyzed the types of motion based on the potential that there is. Right? The difference was, what was really the difference?
Yeah, but
we didn't have that.
Yes,
This was. If we did it properly, this term was not. That's making a huge difference. You see it? Questions? Oh, you guys at the back, you're quiet. Okay. So I'm going to post shortly the next problem set. And if you have any problems and questions, that's the time. So guys, the semester starts, we start to see the end of the semester approaching, right? We have how many? 4 more weeks, something like that. So and things are built up upon what we did. So it's a very good timing now to make sure that you review, you're still far enough from the exams that you don't get too stressed by the coming exams. And it's early enough that if there's something which you don't fully understand, it's time to catch up and make sure that you know black holes or white holes in your knowledge. Everything is there. All right. If no further questions, we're going to resume this discussion on Sunday. Right? Have a good weekend.
אני ראיתי משהו בדוגמה כאילו קלאסית בכללית וקטור לפלס רונגה משהו.
שזה מה?
יש וקטור קוראים לפלס רונגה משהו, רונגלנס או משהו כזה. יש כאילו כזה קבוע תנועה שמתאר הכל, יש לו מקביל כזה ביחסות כללית? כאילו זה
יש משהו, יש איזה משהו